Okay, so we're going to look at chapter 21, which is on musical sounds. And so this is a pretty short chapter, but let's look at the first thing, which is about sound intensity and loudness. Okay, so intensity is the way that a sound strength is measured. Intensity is used for intensity of forces, intensity of sound, intensity of light. So it's a general purpose measurement of the energy per second that's involved. Um, and the thing is, it's measured in watts, but it's also got an area component. So if you imagine these speakers are 100-watt speakers, so they're putting out 100 joules of energy per second, and that's radiating around them. Then you can see as you get further away, that 100 watts of power would get spread over a larger and larger area. And so that's how come this is measured. The loudness or intensity at a point is not just the original 100 watts, but how it spreads over how strong it is at that point, which means you have to think about the entire area it was spread around. So the units are watts per meter squared. And intensity is proportional to the distance. It's an inverse relationship and an inverse square relationship. So if the distance is twice as much, so if this was 1 meter and this was 2 meters and this was 3 meters, then what would happen is that the intensity at 2 meters would be 1/4 as much as at 1 meter, just like we looked at the inverse square relationship for gravity. So it would be 1/4 the energy at that location, and at 3 meters, it would be 1/9 the amount of energy. So 1/9 out here, 1 over the distance squared, 1/4 the intensity I0. Okay, at these different locations. So anyway, so yes, so that's something. So it's power divided by area. Okay, now that's one way to measure it, and that's the way scientists usually will measure it. But notice that the lowest sound a human can hear is 10 to the minus 12th watts per meter squared. That's a very, very tiny amount. And it's such an awkward number that they decided to come up with another way of measuring sound level or loudness. And that's using a scale called decibels. And that was named for Alexander Graham Bell, the inventor of the telephone. And he was always interested in sound, especially because he had a sister who was deaf. Okay, so let's go look at this chart on the next page. And so this one's from your book. And what it's showing is that you have an intensity scale here, and you have a sound level scale here. And so one's in watts per meter squared, the other one is in decibels. And so the intensity scale, as you go from the threshold of hearing, the lowest sound that you can hear, that's 10 to the minus 12th. A whisper is 10 to the minus 10th watts per meter squared. And quiet conversation is 10 to the minus 6th. Well, from here to here, that's 1,000,000 times less sound energy to go from 10 to the minus 6 to 10 to the minus 12. But most of us don't think this lowest sound we can hear and the conversation in a home would be 1,000,000 times louder. So the scale doesn't really fit well with how we think about sound because our ears are so good at hearing. We have such a huge range of sounds that we can hear. So you can see that we don't actually get to 1 watt per meter squared till we're way up here by an air raid siren. And so yes, so the sound levels are very, very tiny. There's not a lot of energy in sound, and our ears can detect huge ranges. Okay, so the decibel level was created to give us a more natural feel to sound. It's kind of like an earthquake rating, which also is based on a logarithmic scale of sorts. So what we've got here is the threshold of hearing is set at 0, but a conversation is set at 60. And a whisper is 20. So these numbers are much nicer to use. An air raid siren is 120. That sounds bad, and it is, okay? But 1 doesn't sound very threatening. 120, that sounds loud. Anyway, so this scale is a lot easier to use. Now, some of the notable numbers on here. When we are close to 90 decibels, that's when we start to actually do damage to our hearing, is around 90 decibels. And at about 115 or 110 is where we actually start to experience pain. So this is damage. And you'll notice they put disco music here. That's actually the pain level. So people start to hurt. So if you're ever in front of a huge speaker at a stage show, the sound can hurt your ears with pain, but also, of course, it can do damage to your ears. So you usually want to make sure that you're wearing head protection, okay, ear protection, headphones or earplugs if you're above 90 decibels. Okay, now, is there a connection between these two? Yeah, there is. And so let's look at that a little bit. Let's say we go from the rustle of leaves to a whisper. Okay, now that is 10 times more energy. 10 to the minus 10th is 10 times more energy than 10 to the minus 11. Notice over here that we have just gone up 10 in the logarithmic sound level scale. Okay, if we go from 10 to the minus 12 to 10 to the, well, let's, yeah. We go from here to here. Okay, we have gone up 10 times 10 times 10. We've gone up 1,000, I'm sorry, well, not that one. 10 times 10, we've gone up 100 times more energy, right? So 100 times more energy. But over on this, we've just gone from 0 to 20. Okay, so as it turns out, there is a relationship here. So 10 is 10 to the 1, and we went up plus 10. When we had 100 times as much energy, that's 10 to the 2, and we went up 20. Okay, now if we go up from, say, 8 to 5, that means 1,000 times more energy, 10 to the 3. And over here, that's going from 40 to 70, that's going up 30 decibels. So there's definitely a relationship. 10 to the 1 is 10, 10 to the 2, we got 20, 10 to the 3, we got 30. And so there is a relationship, and there is a formula for it. But basically, yes, for every 10 decibels that you add, the energy goes 10 times greater for the sound. Okay. Now, I went to an ice-breaking ship, which you can tour over in Mackinac City, and it's there to break ice in the Great Lakes. And it's very, very powerful, the engine, so that it can break through ice. So the engine room has all these signs around saying, hey, you can damage your ears, and telling the rules for how much protection you need and how loud it is at that point. So here you can see that if it's less than 85 decibels, you don't have to have any protection. But 85 to 108, you better have earplugs or muffs. And 109 to 118, you have to wear earplugs and earmuffs. If it's greater than 118, then you need earplugs, earmuffs, and an administrator in there to make sure that you're taking breaks and wearing your equipment. So in this location, it's 93 decibels. So in that case, they would need to wear earplugs or earmuffs. Okay, so it's a little bit above the where you start to get damage in your ears, and you'll know you're getting damage if you start hear ringing. Well, ringing in your ears. Okay, so this will happen sometimes after a loud concert, um, or if you've been in a noisy place, you'll start to hear that ringing. That actually is damage occurring to your ears right then and there. Now, also in this ship, I took pictures of the earplugs. This was a giant box, several feet high, full of these earplugs. And these are good earplugs. If you go into like Walgreens to get earplugs, they'll often be only like 10 dB. They only cut it down by 10 dB, which means they cut it to 1/10 of the sound energy, which is good. But these are 33 dBs. So how much do they cut it out? Well, remember we looked at how 30 decibels relates to 10 to the 3, or 1,000. So when you subtract away 30 decibels, that cuts the energy down by 1/1000th. Now, 3 dB is something you might see. It's very standard for when you buy sound equipment. You'll have 3 dB filters, and that cuts out half the noise. So 3 dB is 1/2 when you take it away. So mathematically it works out to that. So that would be 1/2. And then you multiply those two together, and so all together that's going to reduce the noise by 1/2000th. So these are much better than the ones you buy in Walgreens, where they're just cutting it down by 1/10. All right, so the higher the decibel rating, the better the earplugs. Okay, another thing that's in this chapter is about what music means. Music has a quality to it, a pattern that noise doesn't have. And so here's here's some noise, here's some music. You can see there's a pattern. Now, we talked about standing waves before. And the truth is, when a guitar plays, it generally plays in the first harmonic. But it also can have additional small amounts of the second, the third, the fourth, the fifth harmonic playing all at the same time. So the string isn't really just going up and down like a jump rope. It's got little extra wiggles in it that are representing all these other harmonics laid on top. So here's showing how a string would look if it just had the first and the third harmonic. It would go up and down, but it would also have an extra triple wiggle in the string. So it's playing both first and third at the same time. And if you can imagine having the second and the fourth and the fifth and all those different harmonics playing at the same time, it would be an incredible thing to see. Now, so a musical instrument plays with more than one harmonic. Well, humans do that too. A normal human voice usually has more than one harmonic playing because of the way we vibrate. Tuvan throat singers are amazing. They are singers who deliberately try to have more than one frequency at a time. And so one of these videos is of a musical group from Tuva, which is Mongolia, basically. And so they tend to sing songs about horses and love and things like that. And they're really great if you ever get a chance to go see them. Also, monks will sing. Tibetan monks are known for their singing, or it's called harmonic chanting, where they sing more than one note at once or chant one more note. And this guy is a young guy who this video, he's great. I think he's in Chicago, and he just is wonderful. He can do all 7 different kinds of Tuvan throat singing. Anyway, Tuvan throat singing, if you're a singer, it's a really great warm-up, by the way. So I do it sometimes. So, you know, often mine's not great, but you start out with a low note, no, and then you add higher notes at the same time, and I can never do it, usually in front of people. So go watch these videos, but it really is a great warm-up for your voice. Okay, so go watch those. I can't do it on camera. Okay. So anyway, so yes, so multiple notes at the same time. And oh, and especially when you're listening to these, you'll hear a thin, whispery ooh sound. That is from their throat. So they're singing low notes, and then this beautiful wispier harmonic comes on at the same time. It's gorgeous. Okay, so anyway, it's not a flute. It's from their throats. Okay. So anyway, so when you hear different musical instruments, one of the ways you can tell whether it's a piano or a clarinet is that the different combinations of frequencies. So one might, for instance, play the first harmonic, and then it'll have the second harmonic that's half as loud and half as much energy, and then the third harmonic isn't working, and then the fourth harmonic does. So the thing is, what you do is you have different combinations that give different shadings of patterns and sound. So you can recognize a piano versus a clarinet versus a violin. They all might be playing the same general note, right? These all peak and drop and peak and drop at the same point. These are playing the same note, but they look very different in their patterns here because they have different harmonics. And so something like a piano has a huge range of notes that it plays, and then it also has a huge range of harmonics, which goes off the chart here. And but anyway, something like the bass viola, it doesn't have a very large number of notes that it might play, but it also has all these harmonics, which are higher frequencies that it plays. Okay, so here's just again showing how these have different patterns. And even if you're playing 2 guitars, the guitars have different different materials, rosewood versus spruce or something, they will have a different sound. Okay, now there's something also you're supposed to know in this chapter, which is about the Fourier transform. I used to write computer programs to do Fourier transforms, but it's a mathematical trick where what you do is you turn a pattern of, say, air pressure versus time. Okay, so like, you know, we were watching like this, something like this. And what you do is you figure out what the frequencies are that make it up. So here we have just a one sine wave. And so that sine wave just has a regular frequency of 40 hertz, let's say. So the Fourier transform of it would just show a spike at 40 hertz. Okay, so it's saying this is a pattern that is just one frequency. And here you can see some patterns here of sound wave pressure from a speaker. And down here you can see a Fourier transform. So here we see we've got the fundamental playing, but at the same time a second harmonic and a third harmonic. And that makes, when you put those patterns together, this cool pattern here. Now, what will the Fourier transform of this look like? Okay, let me put in a working slide. Okay, let's go back and look at, so the The idea is that the Fourier transform has some sort of amplitude measurement, and here will be frequencies. Now let's say that this fundamental frequency is 100 hertz. Then we know that the second harmonic is going to be twice that, 200 hertz. And the third harmonic is going to be 300 hertz. So we've identified the three frequencies. Next, let's get the amplitude. So you could actually measure this. Okay, so let's say that this amplitude is a 6. Okay, so that tall. All right, so then we go down here to our chart. At 100 hertz, I would put a spike that is 6 long. What I should do is change colors here. Okay. All right, and then let's go back to look at this. Our second harmonic is maybe half as high, maybe a 3. So it's less energy put into the second harmonic. So at 200 hertz, it would only be half as high. And then at 300 hertz, looks like we're down to maybe just 1 high. So we would go back here and say, okay, this one is only 1 high. All right, so that's the idea. That's what the Fourier transform would look like. And so if you had been able to go to the lab, you would have been able to use the recording to make some Fourier transforms. So here are some that I made. Here's a pure tone voice. So this would be like a folk singer going, just very clear, one note, one frequency, right? So there's one frequency. Panpipes usually are, you're playing one frequency. Basically, there are a couple of extra frequencies in there. But yeah, there's a lot of energy in that fundamental frequency. Now, this is a voice with lots of harmonics. So when people sing like opera, which is some of the stuff I've been trained in, then what happens is you're supposed to let your voice go and shake your body, and you're supposed to let all those frequencies come out. So then you sing like, as opposed to, so you hear the difference? There's one note in that second one, but then there's lots of other vibrations and frequencies in there. So you can see that there might be a lot of energy in the fundamental, but then this one has pretty good energy in the secondary also. And here's the third, and a fourth harmonic, and a little stub in the fifth. And then there'd be the sixth, seventh, eighth, ninth, and this is like maybe over here in the 10th harmonic or so. Got a little bit of energy there and a little bit here. So anyway, so that's what gives the richness to that voice. And some people don't like opera singers at all, but there are a lot of folk singers and jazz singers who also use that technique of having lots and lots of rich notes with their voice. And here's a train whistle. So the train whistle, not a real train, but these little toys, they have holes drilled in them at 4 different lengths. So when you blow on it, you get 4 different frequencies at once. So you can see how this is not the train whistle. That one is the better one. That's at the college right now. So anyway, but you can see there's 1, 2, 3, 4 different fundamental frequencies. And there should just be a guitar there. Where's my guitar? Oh, well. Okay. So anyway, let's go back up to here. Now, sometimes sound reflects and you don't want it to reflect. So when you want to keep sound from reflecting, you trap it in a rough surface or cloth, foam. And in this case, this studio here, they really want to make sure no sound gets out. So they make triangular foam. And so the sound goes in and it gets absorbed in the foam and it can't reflect back out. So you just hear the sound of the oboe. You don't hear the echoes of the oboe. So the sound may come in, but when it hits, it scatters and can be absorbed. Now, so you might think all recording studios are like that, but they're not. This is the recording studio, which is very famous, the Abbey Road studio, and that's where the Beatles did their recording. But a lot of artists only will record at Abbey Road. For some reason, the room has these amazing acoustics that actually make your music sound better. And so here you see they've shoved a whole orchestra in here. This is where the London Symphony Orchestra does their recording. And so they did the Lord of the Rings here, Star Wars, Harry Potter, Call of Duty, Black Ops 2. Anyway, so all that wonderful music was recorded in this studio. And you can see that it's got some sound dampening stuff. It's got some walls with some foam on it, but it also has some wood walls and a hardwood floor. And it does have some baffles up here in the ceiling, but it's like half foam and half not foam. And for some reason, it's just perfect for recording sound. So anyway, so oftentimes people are trying to block sound, and unfortunately, a lot of restaurants have done away with cushions and curtains and things like that. So there's a lot of noise sometimes. And if you have to raise your voice to talk to the person across the table from you, that means that the restaurant is actually already around 90 decibels. So it's already nearing the point of damaging your hearing. There are restaurants I won't go to. They're just too noisy. So anyway, so you can see how someone has attempted to put in some cardboard dividers here to help absorb sound. This vertical garden is in Madrid, and it was put in because sound was reflecting off this wall from a freeway to an apartment building. So now with the vertical garden there, then the sound gets absorbed. Anyway, so it's kind of cool, but everybody has a different voice because we have different harmonics in our voice. And so we all sound a little bit different. Now, a phonograph record will record all the curves of the original analog recording. So that's analog. But of course, most of us now listen to digital recordings. And what they do to make digitals, they take little samples from the analog, and how often they take them usually gives you a clue about how good the quality is, because you're just taking samples. So you want them close together so that it's very much like the analog signal. And then those are recorded into a CD with grooves and pits, and then they can be read with a laser. So a laser is reflected into those. And regular DVDs use a red laser. Blu-ray discs actually use basically a blue laser. It's a higher frequency, so it can detect smaller variations. Okay, so that makes it more precise, so it's more accurate. And so basically the laser beam is focused. It hits this splitter, which allows some light to go down to the detector. Some goes up, bounces off the disc and back and rejoins, and they'll be out of phase now. And the detector detects how much they're out of phase. And so it will detect the presence or lack of sound, and that will give you your frequencies. Anyway, one of the best, most fun videos to watch is this cymatics. So make sure you watch cymatics. It's an amazing video where they're trying to show some of the physics behind sound. And so it's a really cool video. So make sure you go follow the link for that. And that's the end of this chapter. So see you next time for chapter 22. We're shifting to electricity.